For my first video for Chapter 7, I'm going to discuss electron configurations for ions. Remember, ions are charged atoms, so this ties back into what I talked about near the end of last chapter, where we were just writing standard electron configurations for neutral atoms. And in fact, the easiest way to go about writing electron configurations for ions is to start by writing what would be the electron configuration for the neutral version of that atom, and then add or remove electrons from there. So, for example, let's start with, if we have NaCl. That means our positive ion is going to be Na+, and our negative ion is going to be Cl-. So for the cation, remember, that's called what we call a positive ion, Na+. Let's start by writing the neutral sodium electron configuration. So we start, again, we just count along the periodic table. So we go 1s2, down to 2s2, then we go across to the 2p subshell, so we have 2p6. Now we come down to the 3s, and that's where we find sodium. And we only have to count once in the 3s to get to sodium, so we just go 3s1. So again, that would be the electron configuration for neutral sodium. Now, we see here that we have a +1 charge, though. Remember, a positive ion means that it had to lose electrons. So, you just basically have to take away the highest energy electron, which in this case is going to be the 3s1. We're only losing one, so we can just write 1s2, 2s2, 2p6, and now we no longer have anything in the 3s, and that's it. That would be the proper electron configuration for Na+. Now let's do the anion, Cl-. So I'm going to use noble gas shorthand, just to save a little time here. So the last noble gas before chlorine is neon, so we can put that in square brackets. And again, I'm going to start by writing the neutral chlorine electron configuration. So after neon, we come down to the 3s, so we have 3s2. Then we come to the 3p, and we have to count 5 atoms into the 3p subshell, so it's 3p5. So that is for neutral chlorine. But this negative ion here tells us that it gained 1 electron. And so basically you just have to put that electron in the highest energy subshell that is not yet full. The p can have up to 6 electrons, and right now it only has 5, so that's not full. So we can just put it there. So 3s2, 3p6. And that would be your answer. And that's how you can basically do it for any ion, except for there is an exception when we come down to transition metals here. So let's look at iron, I suppose. So if we start with iron, again, I'm going to start with noble gas shorthand. So the last noble gas before iron. And I'm going to go iron, I guess iron 2+ to start. Okay, so the last noble gas before iron is argon. So then after argon, we come down to potassium in the 4s2. Right? So we say 4s2. And remember, the N value, this number right here, for the D block is always 1 less than the row. So right after the 4s2, we now have the 3D. We count 1, 2, 3, 4, 5, 6. So it's 3d6. So that's for neutral iron. Now, the reason that the 3d is written after the 4s is because it is higher in energy. However, transition metals are a little different in that they will always lose their 4s electrons before they lose their 3d electrons, despite the fact that the 3d is higher in energy. So iron 2+ means that it has to lose 2 electrons. We have 2 electrons in the 4s subshell, so we're actually going to lose those first. So we basically kick that out of there. So our final answer for the electron configuration for iron 2 plus would be argon 3d6. Now, if we were to keep going, so let's say we had iron 3 plus. Well, of course, we lose the first two from the 4s again. But now we no longer have the 4s. Now, from here on out, we just follow the normal rule of going with the highest energy electrons. So now we would just take one away from the 3d. Because even though we're taking 3 electrons away, we already took 2 away from the 4s, so there's only 1 left to remove. So now that would become argon 3d5.